No, that was me before I discovered that I needed glasses. I would always just be like, a bit like
I
rush.
just broke my last pair. I've been so busy.
How'd you break? Legit one time. Legit one of my pairs of glasses broke because my parents, they were going to like get the lenses replaced or something, and legit they had the window open and it was up on the dashboard, and when they turned they straight flew out the window. And the funny thing is they pulled over to go get them, right? And the like, because they weren't like destroyed or anything, and then the moment they went out to go get them, a giant truck ran them over. They came home and told me that, and I'm like, no, that didn't happen. You're making this up. It's legit a cartoon scene. Like, you guys are lying. You made that up. Like, no, here. And sure enough, there's some destroyed ass glasses.
Tread, you can see the car. Yeah, but they're staying actually in there.
I know.
Yeah. Well, I can't stop. So,
Yeah, that's really odd.
or I get home and I have like 4 hours. Yeah.
From,
Yeah.
no, like, actually, that's, unless maybe when like, say a lot. I'm in a tutoring if I have a specific reason to wear that, so every day is almost like a letter.
Comparatively.
I mean, granted, I mean, it's maybe, 2 hours, 4 hours.
There's always the more they checked up.
There's always something.
There's always some more that you can put.
This man lives that legacy.
I know.
Okay, you live it more than me though.
Is it good?
No. No, I aspire to be that.
I wish.
I aspire to it. Does that mean it happens? No.
All right, let's get started. So make sure if you turn in your homework last week, chapter 17, I have a no name up here. So I'm not sure whose that is. And so then, of course, we have volunteer opportunities. So just a reminder, right, we're at week 9, so that's kind of scary. Yeah.
Keep
I think because we're all in a panic. And so, right, I have a few volunteers for kind of the first few dates. But if you're still interested in volunteering, this will be going on towards next quarter as well. So you can still get those 10 points for next quarter. So keep that in mind. And again, you can email me if you're interested. And so, yes, it's week 9. And so that means our last lab is this week. And so it should be a fun one. I'll maybe talk about it at the end of the lecture a little bit. And then next week in lab is our practicum. And so it should be, kind of similar to last year's. Not a lot of like in-person lab stuff, but like, questions representative of what we've learned. So there might be a plot, the Lineweaver-Buck plot, Lineweaver plot, right? Figuring out the KM from that if you're given the data, stuff like that, figuring out so today's lab will do figuring out how much your concentration is based off of course, a calibration curve that you're going to make. So maybe that could be another question, right? You're given the calibration curve, you're given the absorbance, and then having to figure out the concentration. So stuff like that. And so I'll get your labs back to you. So I need to grade a few labs that I have. So I'll just keep trying to get those back. But then if you want to hang on to them for the practicum, you can turn them into me after the lab practicum, since I probably won't have too much time to grade between this week and next week, but I will try. So if you want things back, I can also give them back ungraded. All right. So yeah, we're almost done with the year, or with the quarter, kind of scary. And so I'm just trying to remind myself what our last chapters are. So we're doing chemical equilibrium today, and so we'll get into that. And then our last week will be kind of more acids, bases, and kind of relating equilibrium to acid bases. All right, so still a lot of math to go. And then this sort of equilibrium math that we're going to start today, it's going to continue on to third quarter. So you really want to get comfortable with it, so get help early. All right, so now let's look at chapter 19 and what we're studying today. And so, right, we studied how fast the reactions go. So we said that was kinetics, right, getting that kinetic data. And now we're going to study, well, how far does the reaction go? And so that's a little bit different and kind of, what we've talked about. So usually we always use, some sort of A, B, gives us some product. And we tend to use, right, this single-headed arrow, so telling us, right, it's all going to be converted to our product. But that's not necessarily going to be the case now in our equilibrium. And so before we get too deep into the chapter, let's just remind ourselves the difference between the equilibrium arrow versus the resonance. So remember, the resonance arrow is the double-headed arrow, so we could use it like in this case where we're showing movement of electrons in a resonance structure. And I should put a charge on here and then move it over. So that's resonance, right? So with our, again, double-headed arrow. And then compare that to our equilibrium arrow. And so the equilibrium should use these two little half arrows with like this half arrow on top. And so this tells us, right, that our reaction can go forwards and backwards, or maybe it doesn't go to completion. So that's our key there with the equilibrium. And so let's kind of take a quick look at some of the relevance of these equilibrium constants and what this kind of means. And so I won't go too deep into this all, but this is kind of interesting. So this is measuring the binding constant of the fetal hemoglobin versus the maternal hemoglobin. So you can see, right, the adult versus the baby hemoglobin. And so the overall point is that the baby hemoglobin binding constant is has a higher affinity for oxygen. And so that explains, right, how then the baby gets oxygen from the mom. So it has to have a higher binding oxygen affinity so that oxygen, right, can cross the barrier between the mom and the baby. And then, of course, right, it has to have a higher binding constant so the adult can release the oxygen, and then the baby still gets that oxygen. And so I'll let you dive into that article. And so we can also just think about regular hemoglobin. And so let's kind of think about at least this equilibrium process. So a little more simple than the maternal versus the fetal hemoglobin situation, but similar scenario. So now we're just looking at how hemoglobin binds our oxygen to make, of course, our complex, right, hemoglobin oxygen. And so let's kind of think about how this process works with this equilibrium. And so let's just start off right in our lungs. So in our lungs, we're going to have a high concentration of oxygen, and then our hemoglobin probably does not have any oxygen bound, right, because it just came from our body. And so, of course, high levels of oxygen in our lungs leads us to form this product, right, our hemoglobin oxygenated complex. And, of course, it leaves your lungs, maybe travels down to your leg, where now, right, we have a oxygen poor environment. And so that would cause the hemoglobin oxygen to, of course, dissociate, making our reactants here. And then, of course, right, that deoxygenated hemoglobin goes back to your lungs and starts again. And so that, again, we have our arrow showing us that this is a dynamic equilibrium process, right? The reaction is going forwards and backwards depending on the environment. And so this is good principles, so we'll get into kind of, this kind of goes with Le Chatelier's principle again. Just stressing our system. And so again, we saw that in our lungs. So high oxygen shifts it right to form our products. And then again, in our muscles, right, shifts left and releases oxygen. And so taking a look at our fetal hemoglobin, so like we saw, the equilibrium constant is larger, so AKA better at binding oxygen. So again, it can transfer over. And so we'll be looking at, again, our reactions. And so, of course, normally when our reaction starts, our reactants are consumed and products are made. And of course, right, we expect our reactant concentrations to decrease and our products to increase, so that's fairly straightforward. And then, of course, as our reactant concentration decreases, the forward reaction rate decreases. And so eventually, again, if we have some sort of equilibrium reaction, then that can cause our products to react and reform our reactants. And this is, of course, assuming that our products are not allowed to escape. So we've kind of mentioned, like condensation reactions. Sometimes we drive off water to just keep that reaction going forward. But assuming that that is not happening, right, then that reaction can go back and forth. And so now, again, we're getting into reactions that can proceed in the forward and reverse directions, and those are reversible. And again, right, that should be noted with an arrow, with our double-headed arrow. So anytime we see that, right, that's implying equilibrium. If we have just a single arrow, right, that's just telling us all the products should be converted, reactants should be converted to products. All right, so there's our reminder of our arrow conventions. And so again, we'll be seeing a bunch of these double arrows in this chapter. And then, then we'll talk about equilibrium. And so once we reach this state of equilibrium, and so once we're at equilibrium, right, this doesn't mean that there's no reactions going on. It just means that our overall concentrations are not changing. Maybe. So let's highlight that here, right? So once we're at equilibrium, our concentrations are constant. But it's important to remember, so in our dynamic equilibrium, right, the rates of the forward and reverse reactions are equal. And so right, they're at the same rate. And again, right, concentrations remain unchanged. So at, the molecular level, there's still reactions going on, right, binding, disassociating. But again, at equilibrium, our concentrations are unchanged. And I think this is a reaction from our kinetics chapter, so just kind of going through this reaction again, we have the hydrogen plus iodine gives us hydroiodic acid, and again we can see how they're in equilibrium. But they're still reforming our reactants, forming products, just at the same rate. Blah, 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 so that's just restating that. So again, just maybe star this point that in equilibrium, the rate of the forward reaction is equal to the rate of the reverse. And then, of course, right, just because something is at equilibrium, this doesn't mean equal amounts of reactants and products. So this all depends on our equilibrium constant, which we're getting to. So again, we're just saying that the rates are equal, but not the concentrations. And so we'll see what this means. So sometimes reactions reach equilibrium after, almost all of it has been converted. Sometimes they reach equilibrium when only a small amount. And so again, we'll kind of dive into this as we proceed. And so we're going to see a lot of equilibrium constants. So this is our another K. So now we have equilibrium K. And so this is pretty important. So I'll highlight this. And so this is just how to write our equilibrium expression. So let me zoom in a hair and we'll go through this. And so right, we just have our general reaction expression. So some reactant A in A moles plus B reactant with B moles gives a C product with C moles and D product with D moles. And then so notice how you write your equilibrium expression. So it's products over reactants. And then write our parentheses is telling us that's going to be a concentration. And so most likely in molarity, but we'll also get into pressures. And there's a little bit of a difference between our K of our concentration versus K of pressure, yeah.
In the text, what I like is they had like a subscript C below K for that constant. And I just thought that would be good to notice because that distinguishes it from color.
Oh. I was thinking, I was like, well, it distinguishes the C from the P, but yeah.
And the P too, yeah.
So if you want to put the little C there, like he was saying, to maybe remind you, that will help. So that C, right, is for our molarity concentration. And then, right, we raise everything to the power that it was in, right, based off of course, the balanced equation. And then I'll just kind of star this, right, always products over reactants. So that kind of gives us a sense, right, based off of our equilibrium constant, how far is it going to completion? And then, of course, right, we can do math and get precise numbers. And so, again, this is our equilibrium constant, and it does not have units. All right, so let's practice. So before I scroll down and reveal So see if you can write the equilibrium expression for this reaction. And so it's a dimerization reaction, or disassociating, reforming. So 2 equivalents of our N2O5 gives us 4 of our nitrogen dioxide and some oxygen. So see if you can write that equilibrium expression. And so now I'll scroll down and reveal. And so did we all get our expression down here? So right, our products raised to our, of course, 4th power from, again, our balanced equation, times the concentration of oxygen, of course, raised to the 1 power, and then over our reactants, squared. So any questions on this right here? It's not too bad, fairly straightforward. All right, let's do another one. So now we have a multiple choice question. Trying to see if you can see that. All right, so go ahead and try to do that equilibrium constant again. And it looks like they gave you a balanced equation, as my double arrow flies away. So take another minute. All right, let's vote. Who thinks A? What about B? I see a lot of hands for B. So anybody like C or D? All right, so excellent. Looks like everybody picked B, so that looks good, right? Our CO2 is raised to the 3rd. Water is raised to the 4th, so there's our products. Over our 2 reactants, so our propane, and then our oxygen raised to the 5th. Very good. All right, so now we can set up our equilibrium expression, so that's a good start. And so, of course, now we can start getting a little bit of information from this. And so, of course, right, what does the value of K imply then when its value is, let's just say, much, much greater than 1? Well, of course, right, if our K is much larger than 1, and now I'm just thinking more simply, right, products over reactants. Well, if it's greater than 1, then it's probably favoring our reactants. And so that's the case in this reaction. So H2 plus bromine gives us hydrobromic acid, and it has a very large equilibrium constant, so 1.9 times 10 to the 19th. And so, of course, this heavily favors our product. And of course, obviously, if it is less than 1, So again, right, think products over reactants. And so now it's saying, right, it's going to favor our reactants pretty heavily. And so that's the case in this scenario. So nitrogen plus oxygen gives us NO. And so this has a very small equilibrium constant of 4.1 times 10 to the negative 31. And that makes sense, right? Otherwise, we wouldn't have a lot of oxygen to breathe if all of this was converted to NO. So that's good that that reaction has such a small equilibrium constant. And then, of course, right, we could also say if it's close to 1, then they're pretty similar. But again, we want to do math to get more precise numbers. All right, so see what we think so far. So read through these statements and determine which one is false. So A, when K is greater than 1, the forward reaction is favored. It goes to completion. B, when K is less than 1, the reverse is favored and the forward reaction does not proceed to a great extent. When K is about 1, neither the forward or reverse reaction is strongly favored and about the same amount of reactant and products exists. Or D, K greater than 1 implies that the reaction is very fast at producing products. So let's take some votes for this one. So who thinks A? B? C? D? I see votes for D or E. And so it is D, right? So our equilibrium is just telling us how far it goes, right? But it doesn't say anything about the reaction rate. So no info. So this goes back, right, this is from our previous chapters, so chapter 17, 18, with our kinetics, where we have to be given kinetic data, right? Because just because a K is much, much greater than 1, right, this could be on a very slow time scale that it's all being converted to products. So we know nothing about the reaction rate, so good job, those that voted on that. And so yeah, no kinetic information. So again, we have to have kinetic data to know anything about that. All right, send some math stuff. So this will help us later. And so now let's see how we can play with our equilibrium expression. So we can write our reaction in reverse. So then that means our constant is inverted. And so let's just go through that, right? So we can see we have this AB gives us CD reaction. So of course in the forward direction, right, products over reactants. So nothing surprising there. And then write it in reverse. So C plus D gives us A and B. So now, right, our reverse is inverse. And so this gives us our first relationship. So our K forward is equal to 1 over K inverse. So that could be useful. And so let's see what happens when we have different coefficients. And so when the coefficients of an equation are multiplied by a factor, the equilibrium constant has to be raised to that factor. And so if we think about this, what if we have this A plus B gives us C? So that's given by this expression. But then let's just say, what if we wanted to double that reaction? So we have 2 of AA plus 2BB gives us 2CC. And then, of course, right, if you're raising something to the power, then it's like multiplying. So we have to multiply, right, and take this 2C and distribute this 2 everywhere, right? So now it becomes C raised to the 2C, A to the 2A, B to the 2B. Or the same as, right, taking our K1 and then again raising it to that power. So then, right, we can say our K1 is equal to K2 to the N. And so then we also have, so we can add our equations together. So if we add equations to get a new equation, then the equilibrium constant of the new equation is the product of the equilibrium constant of the old equations. And so, right, let's say we have a system of reactions. So A goes to B, and then B goes to C in a separate reaction. So then we can write out, right, our two equilibrium expressions. So our K1 is products over reactants, so B to the B over A to the A. And then, of course, K2, right, is C to the C over B to the B. And so if we want to know A to C, then we can multiply these two together. The B's cancel out to give us our relevant expression. So K3 is equal to K1 times K2 for adding. All right, so let's see if we can take that and play with that, what we just went over. And so, of course, we're looking at now our Haber-Bosch process. And this is a good one to look at equilibrium with. And so we have nitrogen plus 3 equivalents of hydrogen give us 2 equivalents of ammonia. And the equilibrium constant for this reaction at 25 degrees Celsius is this number. So see if you can calculate the equilibrium constant if it's in reverse and then by half. All right, so what do we do to our K? How are these two equations related? What were your thoughts?
Well, the order of the reactants and products is switched, so take the reciprocal of the K. And then they're all multiplied by a factor of 1/2. So you could just take the square root or the power of 1/2 of the constant for the first equation.
Excellent. So is that what everybody did? So it flipped and then times 1/2, so meaning take it to the power. And so let me plug that in. So do we all get this number for our new equilibrium constant? So now our K for this reaction, or K prime, as we're calling it, is 0.003134. Again, unitless. Any questions on this one? Feeling good. All right, so let's kind of try that again. So let's see if you can predict the equilibrium constant for our first reaction, given the equilibrium constants for our second and third reactions. So start walking me through. So how could we add these two bottom equations to get our first one? Did we figure that out? Any thoughts? What did you do? So I guess how can you add, though, K3 and K2, or the reactions of those two, to get K1? Because you have So it sounds like we could inverse K2. So is that what we did? So let's inverse or flip, right, our reactions. Let's just write that out first of all, so we can all be on the same page. So that gives us CO2 plus H2 gives us CO and H2O. So now this is 1 over K2. This is more for my sanity. And then did we just add K3 to it? And the only reason I'm saying that is I'm noticing, right, we have same product. So what if we add K3, so that's CO plus 2H2 gives us CO2 and H2. Oh, sorry, I read that wrong. Sorry. Gives us CH3OH there. So methanol. And then, so we want to verify, is this our equation that we're looking for? Does this match with 1? And so let's see. So we have 3H2, so that looks good. And then CO, so this cancels. So we have CO2, so that looks good. And then our products of water and methanol, right? So that looks good. And so this is K3. And so now how do we get our K1 from these expressions now? What's the last step? Yeah.
I'm not sure. I'm really confused because can't you just do K3 divided by K2 to get K1?
I guess how would you get that? So
On the previous page, or the previous, yeah, it says that, like when you're determining, it literally says that K3 equals K1 times K2. So I just solved for K1 and I checked it and I got the same answer. Is that just happenstance or? What the,
That's how I understood it as well.
Yeah.
But I don't know if it's the wrong answer.
I guess I'm confused too, but
okay, so if you take.
because it ends up being that expression, but yeah.
If you take 1.4 times 10 to the 7th and you divide it by 1 times 10 to the 5th, you get 1.4 times 10 to the 2. And if you multiply that by 1 by the K2, you're going to get the K2.
So it's like two different ways to compare this.
Like this is like algebraic, like I wasn't even looking at the chemicals.
Yeah, I guess I'm confused though, because you need to look at the chemicals though to make sure that they add up to this expression. So I think it just so happened that it was like easy to do that, but we weren't sure, right? Because what if we had added them and we had to like multiply by 2 or divide or something? So I think that's my only kind of precaution, because we have to make sure that they're adding up, right, to give us our K1. Yeah, it's not established yet, so maybe that's where the disconnect is, because we're not sure, right? Because we said that if they do add up, that we can just multiply them, right? But since we're not sure, though, that they were additive. So I think in this case, it just so happened that we just had to flip and add them. And so it looked kind of simple, but yeah, I just want to caution people,
And
like,
so when you're adding the equations, you're multiplying their K's.
yeah, which I think is how people got to that, but I just wanted to make sure that we're kind of making sure the equations add up to what we're looking for, before you start dividing and all that good stuff. Does that clarify things, hopefully? So then we do end up with just K3 divided by K2 from our expression. And I think you said it gave you, what was it, 1.4 times 10 to the 2?
Yeah.
Which is indeed the answer. So I'll just write 140. So any questions on that one? We clarify that. All right, so then let's kind of see the differences in our equilibrium expression. And so usually, like I said, we're usually in solution world, but we can also, of course, apply the same thing to gases. And so it starts off the same. So right now, this is just saying if we had, a gas, we could express it like this form. And of course, instead of concentration, right, this would be pressure or partial pressure, right? Pretty much the same thing, just whatever your pressure is in. So that's straightforward. But we might want to go between our Kc and our Kp, so going between, right, molarity concentration versus partial pressures. And so, right, our values then of Kp and Kc are not necessarily the same because of our difference in units. And so then our relationship is as follows, should we need to convert, where our K pressure equilibrium is equal to our Kc concentration times RT to the power of N. And so the R that we use is the 0.0821, so that's for our liters, ATM, moles, constant. So right, not using joules, so that's why we're in this one. And then it's to the power of our change in N moles. And so again, we'll go through this, but our N is the difference between the number of moles of gaseous reactants and the number of moles of gaseous product. Because we'll see, right, if we kind of create or lose gaseous moles, right, then that's going to have a change on our concentration effect, so that's where it leads to a discrepancy. And of course, T is in Kelvin. I should state that. We should be able to tell that from our gas constant, but good reminder. And so now let's try this. Oop, and it lost its arrow here. And so we have nitrogen monoxide is a pollutant in automobile exhaust, and it's oxidized to nitrogen dioxide according to this equation. So 2 equivalents of NO plus oxygen gives us 2 of nitrogen dioxide. And so it has a Kp of 2.2 times 10 to the 12. And it says find the Kc for this reaction. So see if you can try that. I'll scroll back up to the formula. So start walking me through your thoughts. So what do we notice about this reaction, first of all? So how many moles of gas do we have on our reactant side? So 3, and then how many on our product? 2. All right, so that looks good. So what's our delta N then? Yeah, it should be -1 though, right?
Because it's final minus
Yeah, so should be -1, so 2 minus 3. So there's our change. And then from there, we just need to plug it in. So 2.2 times 10 to the 12th is equal to, so we're trying to find Kc. And now our gas constant times our temperature, which we had to convert. So that's 298 Kelvin. Then all that to the power of -1. I don't know why. 298, thanks. And so let's see, so start punching it in. So help me with the algebra. So is that what we got for the KC? So I saw, oh, there we go, more nods, thumbs up. Excellent. And, oh. So 5.38 times 10 to the 12th, or 13th, sorry. Any questions on that one? And so let's look at our little multiple choice question here. So pay attention, of course, to the states. And so see if you can figure this one out. So in what reaction does your Kp equal your Kc? So does anyone think A is the answer? What about B? Any votes? So some votes for B, so we'll take a look at that. Any votes for C? And so let's look at B again. So we said B was the answer, so do the reactants and products have the same gas moles? And so we have 3 moles of gas on our reactant side, and then 3 moles of gas on our product. So yes, B is the only one. And so we could compare, so A, right, had 2 versus 1 mole, so that changed, and C had 0 versus 2, so of course that was also different. All right, this is probably a good point to take a little break, so maybe like 10 minutes-ish, try to be back at 12 or 12:02, and then we'll continue on with equilibrium fun.
Never mind.
Is it yours?
Yeah,
Oh,
I was thinking
yeah,
cross
could you
product.
put your name on it and put it up there, 'cause I.
No, you guys still have to do it. You guys still have to do it. Yes, yes, they have it only on the first floor. Wanna take the elevator? See, if I'm not in class, it just doesn't exist. That's how it is. It's like, still like that project team.
Oh, yeah. I always forget, but it is May. Yeah, if you email me, then I'll remember better.
I just understood this. That's baller. Oh. Oh, yeah, no, I see. Exactly, that was like, I just saw this morning.
Like, they didn't see the goal.
I called it, did I not?
do, but it's always that much more. So like, it does, it doesn't have a lot. Yeah. I'm not letting pages. Oh, it's not just, here's some extra things on top of that.
We had like 5
This
I
is to
walk
help
over
your,
there and I'm like,
this is to help you with the conversation. It's like, I feel like that
like all the way to the beginning with the particular is the electric stuff where it's like, yeah, that made this, that was made that made. I got that, but like I couldn't explain it, but just be like, okay, I can do this.
it's kind of cool. But then they add extra. At this point, it's just really, it's just really helpful.
You go from math is numbers to math is letters to math isn't even English. It's like English. It's all Greek. I'm like that he gave us because it was like I like how it's spelled out in like very exactly. This is what all the things are.
Yeah.
I'm not gonna. I can just look at this.
And
Usually I'll like write out the equation and then I'll have all the terms next. I don't want to do the presentation. Just put it in like a little notes pad where it's like, oh, you can use this for this.
And then when they ask me questions, I'm always like, what? What did you say? Like, I have to do it before I start, and I'm like, it is last year, or is it before? I literally don't know. But I will.
But then you're gonna wanna take like. All the, yeah.
Oh, I have.
That's what I'm telling you, man. This is why I do this shit.
And then there was like a mistake that was made and then he went back and like redid stuff and at that point I'm like, okay, I can't follow now and now what I should have spelled. You just know what there is, but then there's actually it's only like
All right. All right, hopefully you had a good break, so now you're ready to go back to equilibrium. And so now we're kind of evaluating, well, what is relevant in our equilibrium expression? And so we bring up this term, our heterogeneous equilibrium. So this is implying we have something, right, in a little bit of different states. So we can think of homogeneous, so that's when everything's, let's just say aqueous, in the same phase or solutions. And so what we find is, so the concentrations of pure solids or pure liquids do not change during the course of the reaction. So this could be something, like in this case, we have water down here. So we're running it in water. Maybe it sounds like bubbling a gas through water. So our concentration of water, right, is not going to change. And this could also be implied to like a reaction, like they're called neat reactions, where you try to not use a solvent, but instead use one of your reagents as your solvent. And so that type of scenario, right, that would not have a concentration, so that would not change. And then pure solids could be, like a big lump of calcium carbonate or something, or carbon reacting, but we'll look at some of those examples. But basically, we just want to think about anything whose concentration is not changed. So that would not be included in our equilibrium expression. So then looking at this reaction, and so just kind of comparing, so we have a gas, so right, that has a concentration, and then two aqueous solutions. And so our equilibrium expression would, of course, be as written, where, again, we do not have the water in our equilibrium expression. So, right, all these, again, have concentration values, including our CO2, which this one, right, would need to be in molarity, of course, to be consistent with that. And so here's another example. So if we were looking at this reaction, so this is taking CO and converting it to CO2 and carbon. And of course, right, carbon is our solid product here. And this is a good kind of visualization. So again, right, it doesn't matter what the size of your pile of carbon is, they still, the concentration, right, is unchanged. And we're looking at our gaseous concentration, right? So that would matter, our partial pressure, but again, this does not. So see if you can write an equilibrium expression for this reaction. Again, taking into account what we just learned. So what do we get for our expression? What was relevant in this example? So carbon dioxide, and then that was it, right? Because this was a solid, this was a solid. So it just depends on our carbon dioxide, so we can do products over reactants, so that just leaves us with CO2. So it's just dependent on our CO2 concentration for our equilibrium. All right, try that again with this expression. Again, see if you can pick out which ones are relevant or not. So we have 4 equivalents of hydrochloric acid in the gaseous state reacting with 1 equivalent of oxygen, also in the gaseous state, to give us 2 equivalents of water, notice the liquid form, and then 2 equivalents of chlorine gas. So see if you can write your expression. We're just debating whether to call like security and be like, where's the guy? We might want to call security just to let them know. Oh my gosh, it's like throwing stuff. Hi, there's a guy who seems to be pretty upset. He's outside of the HEC building on Riverside and 8th, but as we can hear him up from my 3rd floor classroom, he's, screaming and yelling. So if you could check that out, that'd be awesome. All right, thank you. Okay, sorry. Just better for your safety to get that taken care of. All right, back to equilibrium. Fun things of the downtown campus, but I won't go into my rant because in truth I love the Medford campus for all its issues, but we won't go there today. What did I do? Sorry. All right, what do we get for our equilibrium expression then? Which one could we ignore? So water, so that did not matter, right? Because again, it's a liquid, so doesn't have a changing concentration, and again, products over reactants, and should have checked if it was balanced. Yes, balanced. So should have gotten chlorine squared over our concentration of hydrochloric acid to the 4th times our concentration of oxygen. Any questions on that one? All right, so now we're going to start moving into more math. So I feel like y'all are pretty good at writing these equilibrium expressions, but of course, right, what do we do with them? And so we want to be able to calculate our equilibrium constant from measured equilibrium concentration. So that's kind of part of what you'll be doing today, or in lab, or on Thursday. And so of course, this is kind of similar to our kinetics in some way, but right, we have to be able to measure the amounts of reactants and products of a mixture in equilibrium. And so we'll see again today, sometimes you can only measure maybe the concentration of some of your reactants or products. And we'll use the principle, so our equilibrium mixture may have different amounts of reactants and products, but our value of our equilibrium constant will always be the same as long as our temperature is kept constant. And so that's going to be really key, so that's going to help us. And so again, right, our value of our equilibrium constant is independent of our initial reactants and products. And so then we'll get into this, so seeing how, of course, we can use stoichiometry to figure out our equilibrium concentrations. And then, of course, right, we can know the change in concentration of one material and then know how much to be in the other. And so again, let's dive into this because it sounds pretty vague right now. But now let's look at this reaction. So we have CO plus 2 equivalents of hydrogen gives us our methanol. And so it says our reaction mixture at 780 degrees Celsius contains 0.5 molarity concentration of CO and 1 molar concentration of H2. And it says at equilibrium, the CO concentration is 0.15 molarity. So what is our equilibrium constant? And so a lot of good information in there. And so I recommend that we set up, they call it an ICE table, but I like using RICE acronym better just because we want to have our reaction in front. And so, right, that's the first thing that we want to write or rewrite. So, okay, we have our balanced reaction. So we said we were looking at this of CO plus H2, gave us our product. And then so the ICE stands for our initial change in equilibrium. So initial, right, they gave us our initial conditions, so we can go back. And so, right, it just says it initially contains 0.5 molarity of CO and 1 molarity of H2. So that's what was filled in down here. And so, of course, right, again, we should not have any products starting off with. You could, but, right, it wasn't stated, so we're just assuming, all right, we're just starting with our reactants. And then, so this change we'll have to figure out in just a second. But we know that at equilibrium, right, our CO is 0.15 molarity. And so then the next thing we want to think about, right, is how much does this go down, and then what's the equivalent, and then how much is created, right? And so what I mean by that is, so right, we're in a 1 to 2 molar ratio. So then our change, which we'll solve for, will be minus X. But then what's our change for H2? It has a 2 in front. Yeah, it should be 2x, so minus 2x. So for every right minus x, we have 2 equivalents of H2 reacting, and then that means, right, our product formation will be what value? If it's 1 mole, what did you say? But it's just 1 mole of product though, right? So yeah, so then x. So does that make sense for our change? So right, this is just based off of our balanced equation stoichiometry. So now we're saying, right, for however much x we lost, we have to form x molarity in product. And so now we can start to work things out with our math here. So let's go ahead and solve for x, right? We can do that. So what do we get for x? Just solving this equation. So x is 0.35, and we're still in molarity, right? And then, so if x is 0.35, so now we can find our equilibrium concentration of H2. So H2, we started at 1, and then minus, so we said minus 2x, so minus 2 times 0.35. So that leaves us with a final concentration of 0.3 at equilibrium. Yeah. So the 0.35 we could get just by subtracting this difference, so 0.5 minus 0.15, so then that gives us our x value here. And that's, right, that's like the only little piece of information we're given. And so you kind of see this in lab too, where it's like you can only measure one of the concentration values and all the rest you'll have to kind of solve for. And then, so that leaves us with 0.35 molarity, right, for our product. And so now that we have all of our equilibrium values, let's write out our Kc, and then we'll plug it into our equilibrium expression to get an actual number. So I'll just start off writing our equilibrium expression. So methanol over H2 squared over CO. So that should feel familiar. And then now that we have all our equilibrium numbers, all we have to do is go ahead and plug that in now. And so now Kc is equal to 0.35 over 0.3 squared times 0.15 . So that's what I get when I punch it in for Kc, about 25.9 for equilibrium. Any questions on this one here so far?
I'm just ignoring the units on that.
Well, no units, remember? Yeah, so K is unitless. All right, let's try that again. And so now looking at this same reaction, so CO and H2. So let's just say now it's carried out in a different temperature. So right, different temperature, new equilibrium constant. And so now we have initial concentrations of 0.27 molarity and 0.49 molarity. And now it's telling us at equilibrium the methanol concentration is 0.11 molarity. So see if you can do this, and then we'll go over it. So let's start seeing what you guys did. So I just set up kind of our initial conditions, right, what was given. So we had our reaction, and then they told us our initial concentrations, again, no product. And then this time, right, they told us how much product we had at the end of our equilibrium, so 0.11 molarity. And so then, right, we could set up our change. So did we get, right, minus x, minus 2x, and plus x again like we did before? And so then what's our x in this case? So excellent. So x is 0.11. And so now with that, right, we can find everything else. So our equilibrium concentration for CO is 0.16 molarity, right? And then this one, let's see, we have 0.49 minus 0.22. So about 0.27 molarity there. So now we have all our equilibrium concentrations again. And we can, of course, plug it back into our same Kc expression. So rewrite that for a second. So now we have 0.11 over 0.27 squared times 0.16. And so let me know what y'all got. 9.4. Let me hear. Other people get that? Excellent. So 9.4 for our new Kc. Any questions about this process here or this question? Yeah.
Can you go over how you do the change like that?
Yeah, so that's just from our coefficients, right? Because we want to see, so basically we're saying, well, they're in a 1 to 2 to 1 ratio. So this decreases by a factor of x, right? This has to decrease by 2x since it's 2. And then this one, now anything on the product goes up. And so in this case, right, it was just up by 1x. But if we had like a 2 there, then we could say like plus 2x, right, for that side. All right, so then we have what's called Q. And Q is more of just like a formality. So I call this, right, let's just call it our snapshot. And so all this is saying is our Q is our snapshot. So basically, let's say we have our equilibrium constant, right? And then we could just take a picture and get our concentrations, right? And so then we want to know from our Q, so we can compare our value of Q to see how far we are from the equilibrium and whether we're going to go forwards or backwards. And I feel like Q sounds more confusing than it is. So right, Q, again, is just the same as Kc, it's just not at equilibrium, right? So does that make sense? So I'll just put right same as Kc or Kp. This is just not an equilibrium value. So again, it's just our snapshot, right? So obviously it's going to have the same formula since it's essentially the same as Kc, but again, it's just not at equilibrium. So our reaction is still moving. And so again, same form. So either we're comparing, right, QC and KC, or QP and obviously KP, depending on our situation. And so let's just think about, okay, well, what is this telling us? So if we take our snapshot, and then if Q is greater than K, then that's telling us, right, we have too many products, so now it's going to proceed faster in the reverse direction, right, to lower our number and go back to K. So again, that's telling us what direction the reaction is going in. So that's the power of our Q, right? We take our snapshot, what are the concentrations, and then, oh, Q is greater than K, so we know the reverse reaction is favored. And so then if Q is less than K, so now that's telling us that it's going to proceed faster in the forward direction to, again, try to reach our K value. And then, obviously, if Q is equal to K, then our reaction is at equilibrium. Sorry, repeat, I just didn't hear you. Yeah, so it just needs to react. So, yeah, it's just, because remember, it's a snapshot. So if it's less than K, exactly, it's telling us, okay, it's still reacting, still moving in the forward direction. And then, obviously, in the more extreme cases, so if your mixture is just reactants, then Q is going to be approximately 0 and proceed in the forward direction. And then if it's just products, right, Q is approximately infinity, and then obviously we'll go in the reverse. And so this is a nice visual representation of all those words that we just said. And so right here's our equilibrium constant K, so obviously at a certain temperature. And so we can, of course, see our snapshot and kind of compare that to our K. And so right now we're at Q is less than K, so obviously, like you guys were saying, that means that it's proceeding in the forward direction. Then it hits here, so our equilibrium point. And then if it keeps proceeding, right now it's gone past the equilibrium, and so then, right, our reverse direction would need to be favored. Any questions about the graph or anything?
The faster, this faster mentioned here, is it the same as the rate? Or just the direction of the reaction?
It's the direction and then just the comparison of the reverse versus the forward, right? Because we don't have any rates, but we're just saying, so down here, right, the forward reaction rate is greater than the reverse, and then over here, the reverse is greater than the forward, so. Good. Any other thoughts, observations? And so, of course, now we get to do some math with it. And so we have our reaction, so iodine plus chlorine gives us iodo-chloride, and it has a Kp of 81.9. And so Kp, they gave it to us in pressures, that's all nice. And so here are the initial concentrations. So our pressure of iodine is 0.114 atm, pressure of chlorine gas 0.102 atm, and our pressure of our product is 0.355 atm. And so first question, right, is it at equilibrium? And then if not, which direction will it proceed at? So try that one out. And so let's start going through it. So first step is just writing out our KP expression. We're squaring our products and then times our concentration of our reactants. Those were just a 1-to-1 ratio. And so then we can plug in our values. So that's 0.355 squared over 0.114 times 0.102. And so what do we get for our Q snapshot value? So 10.4, oh, sorry, 10.84, can't hear, 10.84 is our Q, and then so we're comparing that to KP. So what can we say about this? Are we at equilibrium? So not at equilibrium. And then what direction is it going to go in then? So forward direction, so right Q is less than our KP, so we'll proceed in the forward direction. Excellent. And again, that's just saying that our forward reaction rate is occurring faster than our reverse. They're both still happening. Excellent. Questions about this one? All right, I think we should have time for a little bit more math here. And so again, we'll keep practicing with the same idea. So we'll be doing a lot of these ICE tables, like I said, next week and probably continuing into third quarter as well, all these same sorts of things. And so then we'll go through all this together, but just kind of the general idea is step one, figure out what direction the reaction will proceed. Sometimes, this is easy if we're given all reactants, we know it's going forward, or vice versa, we're given all products, we know it's going backwards. Otherwise, we might have to compare Q to K. So that's the first trick. And then we want to define all changes in terms of X. So again, just comparing our mole-mole ratio. So using our coefficients for our coefficients of X, like we've seen before. And then solve for X. And so sometimes we can approximate. So I think we went over this approximation when I showed you how to do the acid-base lab part, but we'll practice this again. And then if we can't do an approximation, then we have to do the quadratic. And for the purposes of our class, again, I know people have fancy calculators that do things for you. So that's fine if your calculator, just solves it. I'm okay with that. Otherwise, quadratic. And so again, we'll be looking at our ICE tables. All right, so let's try this one. So now we have, what do you know, another dissociation dimerization reaction. Shocking. So I know, and it's always nitrogen and oxygen. So we have dinitrogen tetraoxide, of course, dissociates to make NO2 in 2 equivalents. And then we're given our Kc expression, so 0.36, and we're at 100 degrees Celsius, so that stays consistent. And so it says it initially contains NO2, so watch that. And it's at 0.1 molarity, so find the equilibrium concentrations of both the reactants and products. So go ahead and see if you can start this on your own, and then we'll see how far we get. So let's kind of check in and see where everybody is right now. So I just set up our reaction. All right, our initial conditions. And then what can we say about the change? What did you guys put here for your change of N2O? So what's the problem with minus X though? So what are you given any N2O to start with? Which direction is your reaction going in? Yep, so then this should be plus X, right? So this was the first kind of trick is do we recognize, right, we were only given product in this case. So now we're gonna be making reactant. And so if this is plus X, this has to be minus X there. And so then this leaves us with our equilibrium expression. So at equilibrium, our concentration is X for N2O, and then 0.1 minus X. Oh, you're right. Good catch. So minus 2X, right, from our coefficient, so that was my mistake. And so minus 2X. So if you got to here, this is a really good point, right? So then the next question is, well, we have to plug this in to our Kc. And so let's start doing that. So then we said our Kc expression is equal to NO2 squared, right, over our dimer. And we said that our equilibrium constant was 0.36. And so now, right, this is turning into an algebra expression. So now let's start plugging stuff in. So then is equal to, so 0.1 minus 2x squared over x, right? So now, oops, now we're here. Oh my gosh, I can't just draw a box today. So this is the next good point, because from here, right, it's just algebra. So now we just have to do the math, aka we're going to end up in a quadratic equation, but we're getting there. And so now it's just algebra fun. And so I'm just going to distribute this to start off, to write it out. So that's 0.01 minus 0.4x plus 4x squared is equal to, and then I just took, right, x, moved it over here, so 0.36x. So all this is, again, just algebra fun. And so now I'm going to move everything to one side so we can get it in a quadratic equation. So now minus 0.36x on both sides. So now I have 0.01 minus 0.76x plus 4x squared equals 0. So that means we can plug this into a quadratic. And so just a reminder, right, our quadratic, so in our form of this, so x is negative b plus or minus the square root b squared minus 4ac all over 2a. And so I'm sure you'll get one answer that's not real because there'll be a negative concentration, and then the other value should be the appropriate value for x. And so again, just algebra fun. And if your calculator has already solved it, you can always share the answer. Oh, oops. So then so far I have this, so I still am plugging stuff in, so 0.76 plus or minus this number, 0.646 over 8. And so let's see. Oh, maybe this gives us two real answers. Let's see. So 0.76 plus and divided by 8. So then I have one value of 0.175. And then my other value and the other one is 0.043 or so. Well, they're both positive, but now we need to check it, right? So now one of them won't match. And so now I can tell it's the higher one, right? So we have x of 0.176, right? Well, that would give us a negative final concentration for NO2, right? So 0.1 minus 2x, I'll just do the math so people can see. So up, right, that would give us negative equilibrium. So that can't be our value of x. So cross that one out, right? So that one didn't work. So you should have one value that doesn't make sense. So then this has to be our value of x, 0.043. And so now we can finally go back, right, and solve for our equilibrium expression. So now at equilibrium, so we had said x was 0.0143. So then at equilibrium, right, N2O4 is equal to x, so 0.0143 molarity. And then our final concentration of NO2, so that would be 0.1 times, minus 2 times 0.0143. So then we should have a final value of 0.0714 for our NO2. Sounds good. All right, any questions on that one? And then what you could do to kind of double check yourself, right, is replug this in to KC, right, and at least kind of see, are you in the ballpark? And so we could do that. So just double check ourselves. So that's squared divided by 0.0143. So yes, we get back at our constant, so that's a good sanity check. All right, that's probably a good stopping point then. So we'll pick up on Thursday, do another practice of that with our equilibrium expression, and just keep kind of working on these equilibrium expressions and how to solve them. All right, I will see you in lab. Also, I think marketing is having an open house or something on the first floor in 127, 129. I just got an email about it. They said there would be free food, so maybe check it out if there's free stuff. And quiz for you. Yeah. And I'll stop the stream.